Greetings, fellow explorers. This is Tony with Fount Systems Network, and we're in pursuit of low-carbon innovations to seawater desalination. This episode is a background, I'll call it background 2, on climate change or global warming. I wasn't real sure if I should do an episode on climate change because there's so much out there already, but if we are in pursuit of low-carbon innovations, then we need to say why that's relevant and why that's important. The subject matter of climate change, if you're already intimate with it, then you probably won't get a lot out of this. But if you're like me and you like to continuously learn and explore, then this will be a good opportunity for you to brush up on it. To get a sense of where we are in our pursuit, I'm going to post a link above, and that's going to be the work plan that I posted previously, so you can see where we are in the process. On the subject of climate change, I'm just going to defer to an expert, Professor Russchenberg at Delft University in the Netherlands. He's put together a 7-minute presentation on the subject. It's pretty dense, and it's part of a MOOC, an online course. I'm going to interrupt his presentation at a couple points just to add a little extra detail to the subject that he did not address in his presentation. So let's get started.
This video on climate change and the water cycle. My name is Professor Russchenberg. My field of expertise is atmospheric remote sensing. I develop methods to measure the properties of clouds and precipitation and their interaction with atmospheric radiation. We do this work to better understand climate change and its consequences for the water cycle on Earth. In this module, we will discuss the empirical evidence of climate change, the physics of the so-called greenhouse effect, sea level rise, global ice cover, clouds and precipitation, and also what can we expect in the future. Let's start with the record of the globally average temperature of the last 165 years, as it is measured above the land surface. In this graph, we see the so-called temperature anomaly, the deviation of the mean temperature on Earth in a given year from the mean temperature of the reference period 1961-1990. Although the graph is based on different data sets and methods, they all agree quite well. We can see that most of the time before the reference period it was cooler, but in the last decades we can see a strong increase in temperature. The temperature trend does not follow a smooth curve. Oscillations in ocean currents, variations of global air patterns, or for instance volcano eruptions, can lead to short-term variations in the temperature trend. It is important to distinguish the short-term from the long-term, or in other words, climate from weather. Climate is somewhat loosely defined as the average weather over a period of 30 years. When we speak of climate change, we refer to changes of the mean properties of the weather. Anthropogenic climate change refers to the impact of man-induced changes. Not only the land surface air temperature has increased, warming was also observed at higher altitudes in the atmosphere, at the sea surface, and the air above the sea. And there's more. We saw an increase of the heat content of the oceans, and an increase of the water vapor in the atmosphere. The sea level has gone up, and finally, the Arctic ice content is declining in the summer. There seems to be less snow cover on the northern hemisphere, and also the glaciers are losing mass. We have seen that water vapor in the atmosphere has increased. Can we also expect changes in the amount of liquid water in the atmosphere? Has there been a change in, for instance, the amount of rainfall? On the left, we see the average change of rainfall during the last century. In the blue parts on the globe, rainfall is increasing, and the brown part is decreasing. If we now zoom in on the last 60 years, we see that these changes in rainfall are happening faster than before. Parts of the world will become wetter and others drier. Now that we have seen the different manifestations of global warming, we can ask ourselves, what is causing it? Already at the end of the 19th century, the Swedish scientist Arrhenius hypothesized that increased concentrations of CO2 may lead to warming of the atmosphere.
So this is one area where I want to supplement the information. As I understand it, and I need to learn more about it, Arrhenius codified a theory that had been in development for some time before him. And so here's a nice reference on how 19th century scientists predicted global warming years before Arrhenius, and one of the earliest dates on here is 1824. So we can see it's a theory that was in development for some time, And already a century ago, scientists had a theoretical grasp on the dynamics of excess carbon dioxide emissions into the atmosphere as a result of human activities. Let's go back to the presentation.
The physical principle is quite simple. CO2 is transparent for visible light, but absorbs infrared radiation. Solar light can pass through the atmosphere and warm the surface of the Earth. In response, the Earth emits infrared radiation. This is partly absorbed by CO2 in the atmosphere. In return, the CO2 emits radiation again, also back to the Earth, where it increases the temperature. Now, has the concentration of CO2 increased? Yes. The American scientist Keeling started a long period of CO2 observations in Hawaii, which was soon followed by others elsewhere. An example of such measurements is shown here. The CO2 concentration in the atmosphere has definitely increased during the time that also global warming is measured. CO2 is not the only greenhouse gas. Other important greenhouse gases are, for instance, methane, ozone and water vapor, each with a different impact on the temperature.
So this will be the next place to stop. Briefly, I would like to show you this as well. In addition to the greenhouse gases mentioned, in a very recent article, World Scientists Warning of a Climate Emergency, this is March 2020, there are 3 abundant atmospheric greenhouse gases: CO2, methane, and nitrous oxide. I never knew about the nitrous oxide. I had to look it up when I read this article. It's from agricultural activities. So I thought that was very interesting and worth sharing. Let's go back to the video. I'm not going to interrupt again.
Now that we have seen that the recent temperature trend follows the increase of CO2, it might be tempting to simply extrapolate this correlation to make a prediction of the future temperatures. It is not that simple. For instance, if you force the temperature to increase by injecting more CO2 into the atmosphere, your system can respond with releasing more water vapor into the atmosphere. And water vapor is a strong greenhouse gas itself and will increase the warming even more. The warming has led to a response of the Earth that increases the warming even more. This is called a feedback. The climate system is very complex with many of such feedback processes. We have to understand these physical processes in the climate system before we can say something about its future development. Let's have a look at the scheme of the energy transfer in the Earth system. It starts with solar radiation, here called shortwave radiation, SWR, entering the atmosphere. On its way to the surface of the Earth, it is partly absorbed and scattered by clouds and tiny dust particles called aerosols. The radiation is partly reflected by the Earth, but also warms the surface and the oceans. Evaporation and convection leads to a redistribution of the energy in the form of latent and sensible heat. Furthermore, the Earth emits infrared heat radiation, also referred to as long-wave radiation, LWR, into the atmosphere. This radiation is absorbed by greenhouse gases, aerosols and clouds before it escapes into space again. The processes are very complex and not fully understood yet. To get a feeling for the significance of the different components of the energy balance, we can calculate the temperature on the Earth, assuming different compositions of the atmosphere. Let us first say that there is no atmosphere. The mean temperature would be around -18 degrees Celsius. If we now include the greenhouse gases of today's atmosphere, it would increase to +24 degrees. And if you also take the clouds into account, it becomes +14 degrees. So while greenhouse gases are needed to keep the Earth from freezing, clouds are there to keep it comfortable. To wrap it up for this video, science has progressed significantly. Every couple of years, the Intergovernmental Panel of Climate Change, the IPCC, issues a report on the level of scientific understanding of climate change. The latest report is from 2013. It is now clear that human activity has led to global warming, due to the emission of the greenhouse gases. The role of clouds and aerosols is less understood, as is the response of the Earth system to the global warming. How much will sea level rise? What will happen with the Arctic and Antarctic ice? And how will clouds and precipitation patterns change across the globe? These questions will be addressed in the following modules of this MOOC.
Thanks for watching that. So I want to make some closing remarks here. The presentation on climate change sets a backdrop for our work. You're aware that governments, institutions, businesses are all working toward reducing carbon dioxide emissions to reduce the risks of climate change. What we're looking to do is reduce the buildup of CO2 in the atmosphere that are caused by industrial activities. And these industrial activities substantially cause this because they burn a lot of coal, gasoline, and fossil fuels as part of their industrial processes. So if at Fount Systems we're looking at low carbon innovations to seawater desalination, then we should be looking at ways to reduce reliance of the industry on fossil fuel for its energy consumption. So let's take all this information and we'll call it an input into our value proposition. We could say that investments must be made to reduce carbon dioxide emissions in order to reduce the risk of climate change to current and future generations. As the world continues to divest from fossil fuel-derived energy sources, implementing alternatives to them will help build resilience in the business model and will also help to create the energy markets of the future. That's it for now. I think I'll have one more background episode on the energy-water nexus, and after that, we'll be able to focus on the first draft value proposition for Fount Systems. Thanks for listening. Hopefully you learned something about climate change that you didn't know before. What do you think? Are there better presentations on the subject out there? Please comment on the video, and don't forget to like and subscribe. Remember everyone, keep exploring, keep growing. I'll see you next time.